नमस्कार, सुस्वागतम, केम छो, आदाबाज, वेरी गुड आफ्टरनून। आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत है, अभिनंदन है। A very warm welcome from me, Anil Bharadwaj, for PRL का अमृत व्याख्यान। Today is the 59th व्याख्यान of the series of 75 episodes, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. Hence, it's a joint celebration of the development of science and technology in India by PRL under the banner of PRL Ka Amrit Vyakhyaan. Today, we have yet another very distinguished Vyakhyaan with us, Professor Michael Meyer, who is a Nobel laureate and is currently emeritus professor at University of Geneva in Switzerland. He is going to speak to us on other worlds in the cosmos, the search for planets similar to our Earth, and perhaps sheltering life. We greatly appreciate and thank Professor Michael Meyer for accepting our invitation and for joining us on today's Vyakhyaan, which is a part of PRL's Platinum Jubilee celebration, as well as Azadi Ka Amrit Mahotsav. I now request my colleague, Professor Abhijit Chakravarti, to kindly formally introduce our Vyakhyaan Karta, Professor Michael Meyer, to the WebEx panel, as well as those who have joined us live on the PRL's YouTube channel. Over to you, Professor Abhijit.
Thank you, Professor Anil Bharadwaj. It's my great pleasure. Everyone can hear me?
Yes, go ahead.
Okay. It's my great pleasure to invite Professor Michel Mayor for the PR Amrit Vyakhyaan. He is the Nobel laureate who got his Nobel Prize in 2019 for the discovery of the first exoplanet, which is a planet outside our solar system in 1995. He is one of the greatest scientists of the known to mankind, and probably you can compare his stature with some of the greatest scientists of early 1900s to 1950s, where one have seen the revolution of the the general physics, quantum mechanics, and other theories in physics. He had done a revolution in spectroscopy and in precision measurements. And as we all know, that Swiss watches are one of the most precise watches in the world. And true to that, he is the principal person who has developed the the technique of most precise measurements that can be possible so far, and which actually has thrown open a variety of planets that are so different from our solar system planets, and that is only possible because the technique that he developed and initiated in late 80s and finally perfected in early 90s, and which gave rise to the first discovery. And following that, he continued to further perfection of the technique, and to the level that we are now talking of sub-meter per second to centimeter per second, and we are very close to detecting Earth-like planets in the habitable zone. And we are very fortunate that in 2013 we had organized a meeting in PRL. January 2013 we had organized a meeting in PRL on exoplanets, He had delivered a talk at our Amrut auditorium, and thereafter he had visited our observatory also. I will just share one photograph of that time. Let me see whether I can share it. No, I can't share it. Somehow it is not allowing me to share. Okay, I don't want to waste any time. Okay, so I welcome Professor Michel Mayor to deliver his colloquium from the Amrut Vyakhyaan. Sir, Professor Michel Mayor, please. Over to you.
Okay, thank you very much for your words. I'm very, very happy to be part of this seminar. As you said, I was already a few years ago in Ahmedabad, and also I visited Mount Abu, and I know that you are looking exactly to contribute to the field of exoplanet. So I'm especially happy for that. So now I have to try to share my screen. Okay. Firefox. Keynote. Partager Keynote. So I hope that you can see my slides. So it's a very general description of what is going on in that field, because so many things happened during the last 25 years that we not discuss everything. So I will try to focus on, at the end at least of my talk, on the possibility to detect Earth-type planet and what could be the difficulties. We are not the first to discuss this kind of question. It's very emotional for me to see that already more than 2000 years ago, philosopher was already discussing the problem of the plurality of worlds in the universe. And more in the same letter, very famous letter of Epicurus, he mentions the possibility that on some of these worlds we can have living species. And before this letter by Epicurus, you have already some reference to discussions similar made already a few centuries before. So it's very evidently it was not exoplanet. It was a general philosophical idea that worlds could exist in as a part of the universe. And if we are moving closely to us, the first image of exoplanet I can find is this an atlas of Doppelmayr 2.5 centuries ago. So you see the old atlas, and if you are looking in the corners, the red upper corner, you can notice that already at the time it was very distant stars was designed with planetary system. It's very strange to see that already at that epoch, people start to consider the possibility to have exoplanets on other stars. And no, if we're moving to modern things, you know that the Milky Way is a spiral galaxy similar to this one. And you can notice on this image some small cloud, pink cloud along the line, along the arms. And this, I will go back to this point, is very crucial in this talk. Our sun is only one star among 200 billion. So in the external part of a similar galaxies. But let's imagine that in our own galaxy, we take a picture with a big telescope on a very, very small part of the Milky Way. And this is what you can see. you see that a huge number of stars like the sun. And the question we have today is to see, do we have the capability, the technical possibility to detect planetary system, exoplanet, orbiting similar to us, these stars. It looks a priori very difficult, as the contrast between the luminosity of the star and the luminosity reflected by the planet is so huge that we have a lot of, it's impossible to directly see this planet, at least for most of the system. It's very interesting to have a look back in the story of this field in the last century. During the 20th century, during the first part of the century, we knew from a long time before that to form planetary system, you need to have a disk of dust and gas surrounding the star. But the theory to explain the formation of this disk was due to a wrong theory. It was the interaction of two stars crossing close to each other. And we know easily, we can do the calculation, that you have the probability to such an event is 0. We do not have close encounter between two stars, or if this happens, it will be very exceptional. This is the reason why very famous astronomers, James, Shapley, and others, during the first part of the century, conclude that the solar system was the only one in the Milky Way. Suddenly, for different reasons, in the middle of the century, the idea changed and realized that the accretion disk, the nebula around the young stars, was just formed by the conservation of the angular momentum. When you collapse the cloud, you have always a lot of turbulence, and you have an excess of angular momentum, and this results in the formation of the nebulae. And the idea changed drastically at the time, and you see this is a logarithmic scale. So we jump from nothing to hundreds of billions of planetary systems in the Milky Way. And I have to give some memory of the critical paper for that. It's a very small letter written by Otto Struve in 1952, that he mentioned that it's strange because low mass stars are slowly rotating. And a priori, when you have the collapse of the cloud, you should expect a huge rotation of stars. And this is not the case for the sun as other stars. So he concludes correctly that the excess of angular momentum was at the origin of the formation of planetary disk and then planetary system. So it's a very simple idea, but it was critical for the change of ideas. So going back to this cloud along the arm of the Milky Way, so this is a very famous one with the Orion Nebula, and this is the site where stars are forming and planetary system. In 1995, the Hubble Space Telescope looked with its good resolution, young stars just emerging, going out of the nebula. And when you take pictures with the resolution of the Space Telescope, you can see in the screen on the left that all young stars are surrounded by a small disk of dust and gas. This is the direct proof that this kind of protoplanetary disk exists, and we have the confirmation that we should have a huge number of planetary systems in the Milky Way. Before, already some hints exist in the infrared, what the infrared luminosity of this disk was already discovered before. So if we have a huge contrast between the star and the planet, we cannot see the planet, but if you are measuring in the middle, you can see that the star is moving around the gravity center of the system. And if you have an instrument precise enough to measure the velocity of the star, you can detect small change of the velocity due to the Doppler effect. And we have granted by the fact that the the spectrum of stars, we have plenty of atomic transition. So the game will be to just measure the small change of the position of all these forests offline. So the content of information in this spectra is huge. So you have to concentrate all the information of this kind of spectra to have one single quantity, the velocity. If you can detect and you can see the velocity versus time plot on the right, upper right, that if you have a planet moving in your direction, no, a star moving in your direction and receding, moving again, and so on, eventually you have something orbiting around, and you can do easily small calculation and determine the mass of this object and the shape of the orbit, the period, and so on. So this is an indirect technique to detect the presence of orbiting planet. We built with some French colleague 30 years ago or something like this, a spectrograph with some feature providing a relatively high precision of the velocity. And we start with Didier Queloz, we start a program to measure something like more than 100 stars similar to the sun. And we were dreaming to find maybe planet of brown dwarfs, so degenerate stars and so on a long-term scale, maybe a few years, because the paradigm, the theory at the time, that giant planets like Jupiter and Saturn and so on should have period longer than 10 years. So this was a surprise of our program, because only after a few months of measurement, we have discovered an object with a mass about half the mass of Jupiter and a period of only 4.2 days. So let's imagine a period of only of 4.2 days. This was a discrepancy of factor 1,000 compared to the theoretical predictions. So evidently this need an explanation. At the beginning, where we were not so confident it was really a planet, so we have decided to wait 1 year and to repeat the measurement to be sure that we still have exactly the same phenomena. And it's only in 95, because the first measurement was made in 94, but it was only in 95 that we have decided to announce this discovery. And today, more than 5,000 exoplanets have been discovered and characterized, not only by Doppler effect, but also by different techniques. As mentioned by Abhijit in the introduction, that we have followed a long series of development of cross-correlation spectrographer, this kind of technique to concentrate all the Doppler information to get only the velocity. And for example, in 77, my first spectrograph gave about a precision of something like 300 meters per second on a 1 meter telescope. Then after LOD, the spectrograph having provides precision enough to discover the first exoplanet was already precise to 13 meters per second. And then we have a very big step, ARPS, already 20 years ago installed at ESO Paranal on a 3.6 meter telescope, and with a precision of only 1 meter per second. And I have to mention the instrument developed under the leadership of Francesco Pepe. It's Espresso, put in operation 2 or 3 years ago at Paranal Observatory, and the instrumental precision is 0.1 meter per second. and is connected to 4 8.2-meter telescope. So it's incredible to see that we succeed to improve the precision by something by a factor 3,000 during the last 40 years. Evidently, more precise is the instrument, you can detect smaller and smaller planets. Today, right now, I will move to a slightly different topic. Is an instrument put in operation in Chile about 10 years ago. It's a sub-millimeter interferometer at 5,000 meters on an altiplano north of Chile. And this instrument is something like 60 dishes of 12 meters with the capability to be expanded with distance as large as 14 kilometers. So with a huge optical resolution. And this is typically the domain of sub-millimeter wavelengths. So to study the cold gas in the universe, formation of galaxies, formation of planets, formation of stars, and so on. So this is a very nice instrument. And you can see this is just a different look on this instrumentation. A few years ago, colleagues observed a small molecular cloud known to have one T2 star, a young star in the middle. This is a normal pictures of this field. But if you use the interferometer, this is what you can see. You see that the star itself, seen with the interferometer, you can see the magnification of the disk with this kind of red annulus, dark annulus in the disk, because the matter collected by a young planet pick all the matter in this kind of torus. And this is the image of the formation of a new planetary system. Evidently, this was so promising that this kind of study have been continued, and this is a set of 20-some objects, and you can see all of them, or most of them, present this kind of feature showing the formation of planetary system, evidently with difference from one another depending on the details. If I go back to my own interest, is a Doppler instrumentation. So this is ARP's instrument. It's a vacuum spectrometer put in operation in 2003 on top of Paranal in Chile. No, not Paranal, last year, sorry, in Chile, and is still in operation and using almost 100% of the 3.6-meter telescope. It's a vacuum spectrograph with a huge thermal control to maintain the precision of 1 meter per second. I would like to describe only one object discovered, because we have discovered several hundred of planetary systems with this instrument. Look at the small graphic on the left here. You can see some red symbols. The radial velocity is a function of time, and every time we did a measurement, you put a red dot. And after 7 years, you can see that you can some change of the velocity of that star. Okay, by high, you can say, okay, we have a long period planet. But when you put all the measurement in the computer, in fact, this is the superposition of the velocity, the change of the velocity due to 7 planets. And what is most remarkable, that one is so close to the star, the period is about 1 day, the mass is 1.5 Earth mass. You have another one 6 days with 13 Earth mass, and so on. So you have a set of very, very tight planet in the core of this system. And this is a typical example that exoplanets planetary system in the universe are not similar to our own one. And other systems, I will not show them, have extremely elongated orbits, what is certainly not present in the solar system. So this is probably one of the most important results obtained by many teams working during the last 25 years. That's a huge diversity of the structure of exoplanetary system. You have extremely short period, few hours. You have extremely large eccentricity. You have a very large planet, more than 3,000 times the mass of the Earth. You have a huge diversity. You have the structure. You have ocean planet. You have lava planet. You have extremely different. This is a good example of the complexity of the planetary formation mechanism. Few years after the discovery of the first one, we have discovered a planet with a period still a little bit shorter, it's 3.5 days of period, and we gave the information to some colleagues we are working with in the US, and it's David Charbonneau and Tim Brown, and they measure, we mention the ephemerid, the exact motion we can maybe have a transit, the planet crossing the disk of the star in between the observer and the star. And Tim Brown had a very small telescope, 10 centimeters, in his garage, and he observes this object, and exactly at the good time, he can notice the small decrease of the luminosity by something like 1.5%. So if Jupiter will cross the disk of the sun, Jupiter is about 10 times smaller than the sun. So the luminosity will be 1% of the decrease of the luminosity of the sun. This is typically what we observe here, a little bit bigger. So it's a planet slightly larger than Jupiter. And the year after, Tim Brown and collaborators repeat the measurement with the Hubble Space Telescope, and you can notice the huge, admirable precision of the measurement when you are out of the atmosphere. And this is typically the quality of measurement you can dream to have when you have a satellite in observing stars. And here, this measurement provides a very interesting test, because if you have the Doppler provides the mass of the planet, the transit provides the size of the planet, so you can easily determine the mean density, and it's only 0.3 gram per cubic centimeter. And this is less than the mean density of Saturn. So this was a direct proof of the reality that we have gaseous giant planet. So you see, because still at the time some colleagues were not convinced that it was really a planet, and evidently this was the start of a huge business to observe transiting planet. And here you have a sketch where you can see the star in yellow. In front, you have the star in dark. So if you measure the decrease of the luminosity at the time, you can measure the size of the planet. Once the planet disappears behind, you have a diminishing of the infrared. So you have access to the temperature of the atmosphere of the planet. But what is the most important is a small ring, blue ring around the star. This is the atmosphere of the planet. The atmosphere of the planet is filtering part of the luminosity coming from the star. So this is the most important domain of study for the next decade and maybe 2 decades, because you have access, when you compare the spectrum of the star with the planet in front or behind, you have access to the information of the chemical composition of the atmosphere of the planet. And this is absolutely fascinating because this provides maybe the possibility to detect biomarker, so signature of the life development. Just to have an idea, it's very strange that we can use the transit as a spectrograph. If you are observing the transit in a wavelength where the opacity is very large, the apparent size of the planet will be large. If at the opposite, you're observing in a domain of wavelengths where the opacity is very small, that the luminosity can go deep in the planet, and the planet will look much smaller. So just measuring the contrast of the transit as a function of the wavelengths, you can determine the spectrum of the atmosphere of the planet. It's incredible, and this is evidently the difference is so small. You need a lot of photons. So this already working for giant planet is still not working for rocky planet because the atmosphere is much smaller. I cannot evidently escape to show you the extreme harvest from the Kepler space mission. It's a 1-meter telescope only in orbit, observing continuously something like 100,000 stars in a small field and obtaining every maybe few dozen of minutes one picture of this field on a CCD, big set of CCD. And after few years, you can analyze the shape of the light curves and you detect a huge amount of planetary system. If you have in this plot, you have some dark black dot. This corresponds to system with one planet orbiting the star. But you can see a lot of objects with colored. The symbol used is with colors. Just focus on the few objects with red symbols. This corresponds to planet transit due to 6 different planets. So you see multi-planetary system. You have 2, 3, 4, 5, 6. No, I believe you have others up to 8 planets. The exoplanets are extremely frequent and frequently in multi-planetary system. Now, just have a look. This is in our own solar system. This is an image of the transit of Mercury in front of the Sun in 2019. So you see this small, very small dot crossing the disk. And this is the difficulty to detect the small decrease of the luminosity of the star due to rocky planet crossing the disk of this thing. And this is much worse. I will show you the difficulty behind this domain. But before, I will just mention and illustrate a measurement made already 15 years ago. And you see when the planet go behind the star, you have also a drop, a diminishing of the luminosity, but in the infrared and 16 micron. And this is because the hot phase of the planet go behind the star, and we have a diminishing of the infrared luminosity, and you have access to the temperature of the planet. Kepler is fascinating instrument, provide a lot of discoveries, but only in the field of Kepler is the North Hemisphere. So we have developed a copy of our first instrument, vacuum instrument called ARPS, to be able to measure and follow and determine the mass of planet observed by Kepler, and mostly focusing on low mass planet, at least a priori low size, small size planet. And most of the time, because we have a lot of guarantee time, on a 3.5 meter telescope in Canary Island, that in fact, here you can notice a plot where you put the radius of the planet measured as a function unit of the Earth's size and as a function of the mass of the planet. And you have a strip, long, a large set of different colors, different curve corresponding to different kind of composition of planetary composition. If you have, for example, a planet made only from iron, you will have the red curve below. If it was only made by water, it will be the upper blue curve. If you have a curve crossing like Venus and Earth, it's a planet with rocky planet similar to our own planet. And you see that every time we measure a new system, you can put the plot here and you can notice that you can observe rocky planet with mass as large as maybe 5 times the mass of the Earth. So before this kind of measurement, people believed that it was difficult to form rocky planet more massive than the Earth. No, we can observe rocky planet with mass much larger. And we continue this kind of measurements. Okay, ARPS provide velocities with precision, instrumental precision, at the level of 1 meter per second. But more recently, we have developed, it's in French. We have developed a new spectrograph, Espresso, installed on the top of the Paranal Observatory and connected with the capability, the possibility to connect the spectrograph to the 4-8 meter telescope, so to have an equivalent collecting area of one telescope of 16 meters. And this was in operation from 2, 3, 4 years, and continue to provide excellent measurements. For example, I don't know if it's published, but it should be published or soon. We have an object with a quarter of the mass of the Earth. So a very small planet, evidently on a short period. This is typically, and the precision, the instrumental precision is 10 centimeter per second. Okay, we can, most of the time we are using only one telescope and not the 4. Just to illustrate, where I have mentioned the difficulty of the related with the transit, but it's also very difficult for the radio velocities, because here you have a small piece of the Doppler, the spectral domain used by Espresso. You see this huge forest of line. So if we are looking for a precision of 8 centimeters per second, so typically the radiation and the variation of the sun due to the motion of the Earth, this is only 10 minus 3 of the thinnest of this line. So it's a very, very small, it's about 1 nanometer, and this is precision has to be maintained not only on one night, but due several years when you are looking for long period planet, Earth-type planet, Earth twin. So this is, you need a lot of technique to achieve this thing. But the real difficulty is the stars. That's the instrument. Here you have a very well-known image of the sun, and in the small rectangle, you can see in the middle at the same scale the size of the Earth. So when you are looking for a transit of a planet like the Earth in front of an object with spots, with magnetic activity, eruption, and so on, you can see that you have a lot of noise providing a lot of jitter on velocities, but also on the transit curve. And the reason why we are looking for this kind of difficult object to be detected is a big challenge for the next generation is, do we have the technical possibility to detect life signature? Obviously, the model we have is Earth twin. It's a rocky planet with a small quantity of water on top, because the depth of the ocean is very, very small compared to the size of the Earth. Why we are so interested in planets similar to the Earth? It's not an a priori biased by our knowledge. Is the fact that life need to have this domain of temperature to have first, for the formation, water is a very good component to help for the next chemical reaction. But what is most important, that life need to transfer the information from one generation to another one, and this is made by the DNA. And the DNA, if you eat the DNA above 120 degrees, 150, depending on the details, it will be broken. So life cannot be transferred from one generation to another one if you do not have the possibility to have the DNA transfer of information. And below -20 or something like this, the chemical reactions are so low that nothing interesting happens. So to search for liquid water at the surface of rocky planet is simply a consequence of chemical and physical needs for the transfer of life from one generation to another one. So the question is life a cosmic imperative? So if you have all the good conditions for the development of the chemistry of life, is life will emerge spontaneously after complex mechanism, evidently, in different parts of the universe. And today, we believe that the techniques can provide the answer. And there is no way to go and see. Exoplanets are much, much too far to have the chance to go and directly observe in situ if life exists. This will only be made by analysis of the chemical composition of planets. And this is why I put some emphasis on the possibility to do transit measurement of exoplanet to get the composition. And then after we will search for molecules related to the development of life. And these are called biomarkers. As I mentioned before, you need a lot of photons, because the atmosphere of a rocky planet like the Earth is very small, and the change of the spectrum when the planet is in front or behind is extremely, extremely small. So you need a lot of photons. And I will mention few instruments right now in development. First is a 39-meter telescope on top of a mountain at 2,800 meters north of Chile. It's not Paranal, but it's not too far from Paranal. And this, let's imagine the mirror, the main mirror is a mosaic, will have 39 meters. And this is not a long-term dream, because it is already in construction. But just to have some feeling of what this means, that here you have a plot of very famous telescope, one with a red mark here. This is a very famous Palomar telescope with 5-meter telescope. built in 1948. And on the same picture, you can see the new telescope with a period the size of 39 meters to be with expected to first light in 2028. So it is a huge change of the capability of collecting photons. And this is an image we have of the site in 2022. It's a huge, maybe you can notice in the middle, you can notice two people discussing in the middle. It's so huge, it's absolutely so huge. Evidently, we cannot escape to mention the James Webb telescope. Evidently, it's only a 6.5 meter telescope, but out of the Earth's atmosphere, measuring the infrared domain, and you can every week or every day, you have new fantastic picture coming from this object with this telescope, and already we have the capability to observe transit with this instrument, infrared transit. And here it's not updated plot of the space project made and already launched. It's not complete, but what I would especially mention is what is called here ESA Plateau. This is a specific huge instrument, huge space telescope to be launched in a few years. And this is specifically designed to study, to search for transit for a huge quantity of relatively bright stars, and also to do asteroseismology to get precise mass of the star. And we will need in the future a huge, huge collaboration to provide the Doppler measurement, because we need to have the mass of this planet, and this will be provided by instrumentation like you are developing yourself on top of Mont Abu, like we have in Chile and so on. So the future of Doppler measurement is absolutely mandatory to provide the good physics and to study the physics of exoplanet. And this will arrive in only few years. And next, I have to thank you very much. Merci.
Thank you very much for your excellent, talk. So I will now invite my colleague Dr. Manas Samal for the question session. Dr. Manas Samal.
Yes, I will try to take out of stop the sharing of the screen. No, I don't know how to do it. Sorry.
You can keep it on if just in case there are questions related to the presentation.
Okay, okay.
Hello, Manas. Yes, yes. Okay, thank you, Professor Abhijit. Thank you, Professor Michel Mayer, for giving a brief overview of the exo world and educating us and teaching us about the exoplanet and where the future lies. I'm sure there will be many questions that to be discussed. So for that, I would like to invite my colleagues who are joined us in the WebEx panel to raise your hands and put your questions. And also in between, we can take the questions from the YouTube whenever possible. WebEx members, please raise your hand so that I can take your questions one by one. I see Professor Bharadwaj. Please go ahead.
Thank you, Manas, and thank you, Professor Michel Mayer, for a very excellent talk and summarizing our achievements in these areas of exoplanets. I wanted to know the current status about the composition of the exoplanets, which we know. How the progress is going on in this direction with respect to understanding the composition.
Yes. Okay. This is typically the goal of our research made in Canary Island. We focus on the relatively low mass planet. So we select objects with small contrast made by the Kepler mission, and then after we try to get the mass with the velocities, and then after you have only opposition in this famous diagram, radius versus mass. So this is typically the source of a lot of study of geophysicists, physics studying the chemical composition of planet, and we have a huge diversity. We are sure that we have a huge diversity, because if you have a planet with a period, rocky planet with a period as short of few hours, it should be a lava planet with melted rocks. And due to the orbital migration, at the time of the formation of the planet, the interaction between the young planet and the disk of dust and gas create a migration, and the planet will spiral towards the center. And this is the explanation of the short period we observe. So let's imagine you have a migration made of Uranus and Neptune. This is mostly water with some pollution. So this planet will finish as what is called an ocean planet. So a lot of work are made by people with a different kind of interest, studying the composition of planetary system. And you have a huge diversity, as we observe a diversity of architecture, period, and plan and size. We have also a huge diversity of chemical composition or structural composition not observed in the solar system.
Okay, great. Thank you. Thank you.
So, Dr. Mutis Srivastava, you can proceed with your question.
Yeah, thank you very much, Manas. And thank you very much, Professor Mayer, for a very fascinating talk. My question is regarding the in the context of the small aperture telescopes, 2 to 3 meter kind of telescopes, which are much larger in number. And such telescopes, being larger in number, are mostly located in the sites which are, in fact, they are not very good. So you can go up to, let's say, up to K band, up to 2.5 microns observations. So given such constraints, the instrumentation, and you have already mentioned about the transmission spectroscopy of the planets. So what would be the suitable instrumentations on these telescopes in order to explore the physics of exoplanet? From the spectroscopy point of view, as well as what is your opinion on the high contrast imaging, something like adaptive optics assisted spectroscopy?
Yes, I still believe that small telescopes have a huge role to play, because, for example, we just contribute to a small telescope in space, Cheops. It's only a few dozen, it's 20 or 30 centimeters. And we just measure, we continue to measure the shape of the transit of known planetary system, but with a huge precision. And let's imagine in the future, when you will have plateau spacecraft, they will provide a huge amount of transiting planet. But sometimes you have other planets in the same system, but not giving some other transit. So we can discover in this system, we can discover additional planet with small telescope, because Plateau main characteristic is try to measure relatively bright and nearby stars. So typically a 2.5 and so on telescope is absolutely able to contribute to these things. For example, Cheops have detected, and this is a small telescope, has detected a lot of new planets not known by the transit before. So I'm sure you see that we operate from something like 20 years, a small 1.2 meter telescope at La Silla in Chile. And we have discovered, I don't know, more than 100, maybe 200 planets with this small telescope. 1.2 meter telescope discovered by transit. No, by transit, by Doppler effect. So I was doing some small estimation at the beginning of this kind of domain. My colleague Jeff Marcy had access to a 10-meter telescope at Keck Telescope, but only 20 nights per year. We have access ourselves to the 1 year complete, 300 nights, but with a 1.2 meter telescope. And so you can compare what is the efficiency of these two kinds of telescope. And we see that, in fact, the small telescope gain the competition in these things. So evidently, if you have access to a big telescope with a huge number of nights, it's better. But it's rarely, okay, 3 meter telescope like we have in Chile or Canary Island is good. But okay, if you have 2.5 and Moabu, I believe it's so almost the same. I don't know what is a typical seeing condition at Moabu.
It's about median seeing in winter is about 1.2 arc second, and in summer it is about 1.4.
Okay, no, it's not bad. It's not bad at all.
And we get about 220 nights, cloud-free nights in a year.
It's huge, huge. Okay, but for spectroscopy, transit spectroscopy, I believe it's difficult. It will be difficult with small telescope. It's probably possible for giant planet. Yes, giant planet is possible because you cannot integrate so long because you have to do the measurement during the transit. So you cannot accumulate the exposure time. So, but after evidently a bigger telescope is better. But I believe that if you can train young people to do atmospheric studies, transit spectroscopy on a 2.5 meter telescope on giant planet transiting, then after they will be formed to maybe to apply to get time on bigger instrumentation. So I believe, and if we consider among my young colleagues here, we have some of them working on the physics of atmosphere, but also you have other people working on how to decrease the jitter due to magnetic activity. This is really the big problem because we have a small telescope, 10 centimeter, working in Canary Island and in Chile, another one, with the capability to measure the integrated light of the sun. And so we use fiber link and we measure with the same ARP spectrograph every day. We measure continuously the apparent velocity of the sun. And you have a curve like this with an amplitude of 1.6 to 2 meters per second due to the magnetic activity. So a lot has to be done to understand the magnetic activity influence on velocities and try to find some trick to decrease this effect. And you have some promising people, promising work to trying to decrease by a factor 2, 3 the noise, apparent noise of the velocity of low mass stars. So this is, I would say, typically a physics mathematical approach for this. You don't need a telescope for that.
So what kind of resolution you will suggest for these atmospheric studies?
If you have,
Resolution of the spectrogram.
personally, I'm working with 100,000. I don't know what is your Paras, what is the resolution?
See, the Paras 2 on the 2.5 is the resolution of 110,000.
But the highest is?
110,000. 110,000.
Parfait, parfait, perfect.
Yeah, thank you very much, sir. Thank you.
Merci.
Okay. Now I invite Professor R.T. Deshpande. Please go ahead with your question.
Thank
Professor
you very much.
Deshpande,
Yeah, thank you very much, Samad. Professor Mayor, thank you so much for such a nice talk. I am not an expert in this field, but I could understand the major part of your talk. And thank you very much for that. I have a few questions. And my first question is that you mentioned that already 5,000 exoplanets have already been discovered. And you also mentioned that when an exoplanet is there in front of a larger star, there is a possibility of understanding the atmosphere of exoplanet. So my question is that as on today, what is our understanding about the atmosphere of these exoplanets? How many of these 5,000 are such where there could be possibility of life? This is my first question. And second question is that are there research groups who are trying to follow these exoplanets where there could be life?
Yes. At the present time, we have several planets, maybe a dozen or something like this, or maybe a little bit more, of planets in this what is called the habitable zone. So in the region where the temperature is compatible with liquid water. But at the present time, all these objects are hosted by very, very low mass stars. So typically you have TRAPPIST-1, and you have another one, I don't remember the name. So this is planet with a star with a luminosity maybe 100 or 200 smaller than the luminosity of the sun. So the habitable zone is much, much closer to the star. So typically the period of this potentially habitable planet have a period of maybe 10 days or something like this. So it's possible to have liquid water, but if it is really good for the development of chemical reaction needed for life development, I don't know, because this kind of very low mass stars are known to have a sometimes very strong flux of high energy particle, and so I don't know if it's really is a good place for life development. So it's the reason why we continue to develop the technique to find planet in the with period as large as few months and maybe 1 year to be further than the star itself. And so planet hosted by star for 0.8, 1 times the mass of the Earth. So at the present time, for example, the James Webb Telescope, comme ça, will devote a huge amount of time to study this famous TRAPPIST-1 planet, because 3 planets are hosted by this star are maybe in the habitable zone. So the search for biomarkers has started, but mostly orbiting low mass star.
Thank you. Another question is that you mentioned about this 39-meter segmented mirror. So would you please tell who is building that mirror? Which company is building?
I don't know. I don't know. All the previous mirror was made by shot in Germany for the 4-8-meter telescope at Paranal, but the mirrors made because it's something the 1000 segment. It's a huge amount of small piece. I don't know. I'm not sure who are doing this.
And my last yeah. Sorry.
If needed, I can ask to some colleague to be.
Fine. No, it was just out of curiosity. I just wanted to know that who is building. Right. Fine. And my last.
Typically, you need to have zero dur. It's a low or zero dilatation glass, and most of the time it's made only by shot in Germany.
And my last question is a little philosophical kind of question. That is exoplanet research. From the scientific research point of view, this is indeed very exciting, and there is no end to research. I mean, scientific mind always keeps on looking for newer and newer thing and exploring unexplored horizons. But as a as Abhijit was mentioning, what is your view in terms of exoplanet research being a scientific quest and the existential requirement in the decades to come? So, yeah, your comment, please.
Yeah. Okay, for me, I believe the most important goal of this kind of research is some kind of philosophical, to answer some philosophical question. What is the position of life in the universe? Is it unique or not? What is our position in the universe? When I say we, life, Earth's life, this is one. But recently, I've been informed quite a lot on the studies made on Mars and Venus, both having suffered from the escape from the possibility of life, and it's maybe a very good training field to understand the worst scenario we can anticipate for life on the Earth. So just studying the history of the atmosphere of Venus and the atmosphere of Mars, I believe we can learn a lot of bad things we can do on our own planet.
Thank you very much for your kindness in answering my questions. Thank you so much.
Merci.
Professor Mayor, one of our YouTube viewer wished to know your comment. How about using interferometric techniques to image exoplanets?
Yes. Okay. We have seen first that ALMA provides the possibility to study the physics of formation of planets, the structure of accretion disk, and so on. But to detect planets themselves, okay, in principle, you can do it by interferometry. But I don't know if it's competitive. Oh, yes, no, okay, sorry. You probably, you have one interferometric technique is to do astrometry. Different kind of interferometry. But astrometry is certainly one very interesting. And I know very well that some colleagues are studying the possibility to do space astrometry. This in the 10 years or 15, 20 years ago, in US, they have a project to do space astrometry to see just the reflex motion of the planet due to Earth stars due to planets. And this start again, the interest for the development of this kind of techniques start again. Already Gaia, the satellite launched 3 or 4 years ago, provide few astrometric planets, but it was mostly massive planet for the beginning. But if we have a specific satellite designed to sort for small astrometric motion, we have maybe the possibility to study the presence of planet for our closest neighbor, because astrometry is specifically efficient to study the closest, the planet with the smallest distance to the solar system. So I'm sure that a few years ago, the Chinese was looking for the possibility to develop STEP, I believe is the name. It was an astrometric mission. So I'm sure that this can approach astrometric mission to detect the reflex motion, astrometric reflex motion.
I hope that answered the questions. The same person is asking what cross-correlation technique you used in your work for detecting exoplanets?
The very first start was an idea provided by Felget in 1954. Then after a very experimental technique was developed by Roger Griffin in 1967, and then after we did ourselves object like this. It's very simple. You imagine, I will describe the first instrument, and then after you can understand the development after. Let's imagine you put a plate in the central surface, focal surface of the spectrograph. You have the spectrum of the star, and you replace it by a small piece of glass coated with chromium, with small hole at the position of atomic line. And then after you project the spectrum of the star on this plate, this grid, and you do some kind of motion, relative motion between both. If the observed lines are just in front of the hole in this small piece of glass, the transmitted light will be very small. This is a physical way to do the correlation. So it's just a problem to move the observed spectrum relatively to this grid. So this is the old technique made 40 years ago. Today, we can do this, and it's much better with the CCD. You record the spectrum on the CCD. You have a very high resolution spectrum, and then after you do a mathematical cross correlation with, you can do with the star itself. You cross correlate the star at different epoch, and the cross correlation function give access to the velocity, the change of the velocity. Or you can have different other possibility to do the correlation. But this is the idea of this kind of thing. It's one way to concentrate all the Doppler information of the spectrum on one single quantity is the cross correlation function of when you have a fit between the two things. It's a fascinating technique because evidently when you have a broadening of the line due to the rotation of the star, you have immediately you have a broadening of the cross correlation function. So you can use the same technique to measure the rotational velocity of stars. You can the quantity blocked by the equivalent widths of the cross correlation function is a measurement of the metallicity, and so on and so on. So we can do a lot of things with this kind of technique.
Thank you. I hope that answered the question. My sincere apology to all the YouTube viewers who have posted the questions. Due to time constraints, I may not able to take your questions. I would like to conclude the question and section by one question. My question to you, Professor Mayor, is that during your discovery of Pegasi B, you selected like 100 stars to observe, right? Yes. So what was your initial thought to select, to select the sample? And after how many stars you hit the Pegasi B?
I did a long survey with one of my old PhD students, Antoine Duquesnoy, of just to study the duplicity of star, solar type star close to the sun. And this was made on something like 15 years. And when we did this study with a low precision, it was with the first spectrograph, Coravel, made in 77. It was not for planet search. And we have selected from this sample 142 stars apparently not in binary system. So this was the result of this old survey we made with another instrumentation. And then after we start, we have no a priori measurements. We measure. And okay, several of these subjects was presenting variability of the velocity. And this was always due to magnetic activity. So we start to learn that we have problem with magnetic activity. And one in this sample was periodic, apparently with a constant velocity, constant amplitude, and a good phase. So this was completely different from the not completely stable stars due to the magnetic activity. And so the occurrence, the frequency of hot Jupiter is not so big. It's about 1%. So in a sample of 100 stars, you are not dreaming to find extremely large number of hot Jupiter. Hot Jupiter is a subject with very short period.
Thank you. I don't see any hands been raised in the WebEx panel. So now I invite my colleague, Dr. Mudit Srivastava, to propose vote of thanks. Mudit, please.
Yeah, thank you very much, Manas. But before I propose my vote of thanks, Professor Nandita Srivastava, the chairperson of our Vyakhyaan committee, has something to share. And she is sharing the pictures which Abhijit wanted to share, I believe, in the very beginning when Professor Mayer with us.
Yes. You can notice in the back, in the middle, a man, one maybe of the highest size, is Francesco Pepe. He was my collaborator, having been the PI of the last and most precise instrument. Yes, it was a very good time.
Yeah, and I would like to add that the place where, in the previous photograph, the place where Michel Mayor is standing is where the 2.5 meter telescope Pyre now stands.
Okay.
Exactly. It was a very nice time. And you can notice at the extreme right, I don't remember the name. This lady at the extreme right.
She was my student, Priyanka.
Yes, and she's working right now with success in Germany.
Yes, that's correct.
In the domain of exoplanet.
Yes, that's correct.
So I'll move to the next slide. Okay.
Yes, thank you, Professor Nandita, for sharing these wonderful pictures. And now it's time to propose the vote of thanks. And Professor Mayer, it has indeed been an honor for all of us. It has been one of the rarest of the rare occasion where we got to hear about the field from the pioneer of the field himself. So it has indeed been an honor and privilege for all of us. Thank you very much. Thank you very much to be with us and for answering all the questions from all the audience. I also thanks all the audience from our WebEx panel as well as from our YouTube's audience for being with us for this much of time. Thank you very much. I would like to express my gratitude to our director, Professor Anil Bharadwaj, and all the members of this Amrut Vyakhyaan committee, Professor Nanda Srivastava, Dr. Bhushit Vaishnav, Professor Lokesh Shahu, and all others who have just made it possible, all the technical teams who have been behind all this effort to organize this lecture and streaming this lecture live on the YouTube. So thank you very much for all the help and efforts. Thanks a lot. And with this, I would like to conclude today's Amrut Vyakhyaan. Thanks to all of us, and we'll be meeting again for next Wednesday for another lecture. Thank you very much.
Thank you.
Thank you.
And have a good result with the new instrument in Moabu.
Sure,
This
thank
is
you.
my
Thanks.
guess.
Thank you.
Thank you for your good wishes.
Thank you.
Merci.